Okay, I think we are up and running. Welcome to the summer semester, you guys. I know that we didn't quite finish the last semester the way we had hoped. So I hope that you still have that um, energy built up from the finals week that we can use for the summer semester. We are going to be talking about a lot of COCO related stuff for the first class or so before we get into the real computer architecture stuff. My goal for today is to tell you guys about how the class is going to be run, talk about the introduction, talk about the books we need, where is the class going to be at, the location, Piazza, the online tools we are going to use for the class, syllabus, and then depending on how much time we have left, we may actually you know um, get into the material for the next class. So let's see how things go. First things first, today is Monday, May 24th, and the reason why we are meeting online just for today is because the COVID tests for the on-campus students have not come back yet. We are waiting for that. I think they're supposed to come back by Tuesday, which means that we can start meeting in person on Thursday, May 27th onwards. What this means is for students who are on campus, I expect you guys to see. I expect to see you guys in the classroom, which is low 4050. Hold up. Give me 1 second. The window is going to be in and out now. Yes, it is being recorded. That didn't quite work the way I was hoping for. Let's see if I can quit this. One minute. Okay, I think this should be fine. If I go back, all right, we are up. Andre, yes, it is being recorded. Let's see. What was I saying? Yeah, so we are going to be in low 4050 from May 27th onwards. So what this means is for students who are going to be in person will be in the classroom, and for people who are online, they are going to be logged in using the same Webex meetings to the same classroom. Okay, let's move on here. The reading for each class is going to be assigned. We have two textbooks for the class. One is based on computer architecture. One is based on operating systems. And for the networking part, I'm going to be supplying slides. But for computer architecture and operating systems, you guys will be expected to have this textbook for reading as well as for certain references, right? So there are going to be several block diagrams that are pretty dense in the content. So for those kind of things, a textbook is going to be very, very handy to have. So the computer architecture textbook is Patterson and Hennessy, the 5th edition, and the reading for today is section 1.1 to 1.5. Let me continue with my introduction. My name is Mahmood Hamid. Most of you have had me for at least one class. Many of you just last semester in COCO. My email address is listed over here. However, I have primarily been using Webex Teams to communicate with everyone. So I guess the quickest way to sort of get my attention is on Webex Teams. I just listed my phone number over there. I don't suppose you're going to use that at any time because I'm not going to be in my office. I'm going to be in the classroom if you want to see me in person. In terms of my office hour, it's going to be on Wednesdays from 2 to 4 p.m. And I'm going to be hosting that on this WebEx meeting personal room. The link is provided over here. Now, we have two members on our teaching staff. One is a teaching assistant, Chibiu Kem, who is here, and the other is Colin Denison. Colin took CANOS with me just last semester, so he's coming fresh with all the content, and I hope you guys will be able to use both these resources effectively to work on your activities as well as for your homework. So I think both of them are online. I see Chibukem online and I see Colin as well. So let me invite Chibukem to introduce himself first. Just say a couple of words about your involvement. Go ahead, Chibukem. We are not able to hear you. I'm not able to hear you. Are others able to hear? Yeah. GBKM, I think you need to. Oh, he's logged in with two devices now. All right. So while GBKM tries to resolve his audio settings, we can maybe look at. Oh, okay, you are back. All right, go ahead. Thank you, GBKM. And the next person is Colin. Colin, are you there? Hey, yes, we can hear you. Thank you, Colin. Now, I suppose everybody knows how to join a space on Webex Teams. Um, and that there are two spaces created for our class, one for Monday, Thursday, 8 to 9, and the other for Monday, Thursday, 9 to 10. The links to those are also provided over here, just in case you need those links if you are new to Webex Teams. However, what I recommend is, depending on how your evening is set up, you can join one or both these spaces. You would have to join them first. Only then you can see the messages and the communication that is going on over there. And the way you join it is simply by going to Webex Teams, right? So I can just maybe show you over here by going to Webex Teams. And if I go to all my teams, these are all my teams that I have. And if I click on CANOS 2012, summer 2012, on the left hand side, you can see a general space, and then you can see two other spaces, Monday 8 to 9 and Monday 9 to 10, right? Monday, Thursday 9 to 10. So you would have to click on that, and then there will be an option for you to join that space, and then you can see all the activity that is going on over there. And the TAs will meet in that same space. All right, questions? So you've got 8 to 9 and 9 to 10 on Mondays and Thursdays. That should give you a clue that things are going to be due Monday and Thursday at 11:59 p.m. Okay. Let's move on. Chibukem and Colin, you guys don't need to be here for the rest of the class. If you're welcome to be here, but you don't need to be. You guys can carry on with your research work or daily classwork as you please. Okay, let's see. What is the class consists of in terms of requirements and grading? There is a graded activity for each class. So every class, just as you had quizzes, daily quizzes for COCO, this is a little bit more involved. We are going to call that class activities. So what typically happens is I will use the first 1 hour or maybe 1 hour 15 minutes of the class for lecture. And then I will leave some time during the class time for you to work on the activity, or at least get started on the activity. Because some lectures tend to go longer than the others. And if it's a long lecture, you might have just a few minutes left over for the activity, in which case you can use the help sessions by the teaching staff to complete the activity. And it is going to be for each class. It's 15% of your course grade, and it is due that same class day. There is generally one homework assignment per week, and I will post the first one on Thursday, and it will be due the next Thursday. Homeworks are also 15% of your grade. And again, even for homeworks, you guys can discuss, but you will be expected to write your own solution. Activities, the same. You can discuss with the teaching staff, you can discuss with your friends, but these are supposed to be submitted individually. There are going to be 3 exams for the class, 2 midterms and 1 comprehensive final exam. For the 2 midterms, it's going to be 20% each, and the final exam, which is comprehensive, it is 30% of your grade. This is just a recap of what I said, most of it actually. So the in-class activities should be uploaded on Gradescope. No late or makeup activities. At the end of the course, I typically drop a few activities. But yes, there is one today, and it is on Piazza. You can work on that. Some part of it today, and maybe the rest after the class in the evening. Yes, there is one today. Let's see. It's assigned on Piazza, and I usually assign that before class. And then you guys will be submitting that before 11:59 p.m. tonight. Generally going to be, basic cocoa material, nothing too difficult. But we need to establish that we all know these things before we continue with computer architecture. We are going to make every effort to grade those activities by the next class day. Now, um, we have 50 students in this class, so I'm hoping that we can grade them before the next class. Let's see how that goes. We will find out soon about how much time it is taking for the TA to grade each activity. Homeworks, again, same rules, assigned on Piazza, due on Gradescope. Please don't be late in terms of homework submissions. And in terms of grading homeworks, we'll try to return them in 1 week's time. So things are assigned on Piazza, due on Gradescope. That's essentially what's going to be going on. Peter asks a question: should we use the original activity sheet for your answers, or are we allowed to write solutions on a separate sheet? Up to you. Um, Either is fine, Peter. Andrew says, is it possible to have the Coco note somewhere just for reference? You should be added to Coco Piazza site, right? So you should have all the Coco notes. Yeah. You will still have access. You got kicked from that? So I made the class inactive, which essentially means we cannot post anything new to it, but we still should be able to take it down. All right. So let's just say this. I didn't mean to kick anybody out. I just wanted that class to be inactive so that we can have new classes be active and then they show up at the top of my list. Are we going to have in-person help session this semester? Probably not. David, I don't think we'll have an in-person help session just because of the COVID regulations, but we will have in-person class. Let's see. Jiajeng says maybe you should click on the show inactive classes. Yes, I know that. I've been using Piazza for a while. Okay, it shows up when I show. Yeah. It shows up when you. Yeah, show inactive classes, and then it'll show you. You should be able to download or look at all the material. You may not be able to post anything new to that page. All right, moving on. Exam dates. Please put them on your calendars. Exam 1, Thursday, June 24th. Exam 2, Thursday, July 29th. And then the final exam is going to be the last day of our classes this summer semester, August 19th, which is also a Thursday. I will be discussing logistics as we get close to the exam days. So, my point being, please mark these dates on your calendar so that we don't miss exams, which are requirement for this class. Okay, now let's talk about the required textbooks. For computer organization or computer architecture, I have Computer Organization and Design by Patterson and Hennessy. It is a very popular textbook for computer architecture. It is followed by many schools. And the 5th edition of that textbook is what we are going to be using. It is available at the bookstore. And this is sort of where we will start the course with computer architecture with the Patterson and Hennessy textbook. The next part of our lectures, we will move into operating system. And when we do that, we are going to change our textbook to Silberschatz, Galvin, and Gagné. The title of the book is Operating System Concepts. I said 9th edition over here, but the 10th edition has also come out. So you can use 9th or the 10th edition. It doesn't really matter. I think the 10th edition is what is available on the bookstore. So if you were taking it from the bookstore, fine, you can take the 10th edition. Because generally there will be readings assigned from that, and when we move into operating systems, you will see that the best way to kind of learn about operating systems is to do a little bit of reading, because there's a lot of terminology that is involved. Um, so it's not possible uh, for me to cover everything about operating systems in the class. So I will be relying on you guys to do a little bit of reading in that sense. What time will be the exams? So right now you should be blocking the class time 8 to 10. However, depending on, I need to assess how many students are in person and how many are online, right? So I will be making that assessment in this week. Once I do that, I can figure out the logistics based off of that. But as a general rule, you should be expecting that exam to be on the class time. It may be longer than that, it may not be. That depends on how many students are in person and how many are online. Let's see. Okay, let's see. Let's move on. Right, and sure, there are going to be electronic copies of the digital copies of the textbooks. You guys are feel free to purchase either the hard copy or the soft copy, whatever your preference is. I personally have digital copies of the book on my iPad, and I can quickly find things and read through them pretty fast. Okay, Piazza and Gradescope. These are two tools that I use a lot. Piazza is sort of my one-stop shop for all the course material, homework solutions, activity solutions, lecture slides before class, lecture slides after class, back exams, solutions. Everything is organized and put on Piazza. So go on Piazza, look under resources, and you will find all these sections. Um, and my guess is most of you have already sort of done that with me on Piazza already. So you should have that. You should be comfortable with that. Gradescope is going to be our submission and grading platform. So all the homeworks, activities, and exams will be submitted on Gradescope, and they will also be graded on Gradescope. I have added all of you to Piazza as well as Gradescope. But if there are some last minute additions, if you have registered for the class maybe yesterday or the day before, then I may not have included you on those platforms. Let me know and I will add you to them. But you need to let me know sooner than later. All right, we are going to be using Webex platforms as well. Webex meetings for lectures and instructor office hours, and we will be using Webex Teams with the title ECSE 2660 CANOS Summer 2021 for general discussion for TA and undergraduate student assistant help sessions. And there are smartphone apps available for Piazza, for Webex meetings, for Webex Teams. So having access to these platforms on a smartphone can be very helpful. So you know it'll give you the ability to be involved in the conversation almost all the time. Now, inside our class, you are invited to create your own spaces if you want to sort of make some groups, maybe groups of 2 or 4 or 6, whatever that may be. You are invited to create more spaces within our class. Just don't do it outside the class, because if you do that outside the class, then other people might be seeing it. Do it within the class. You don't need to add me or the TAs to it. I will be able to see the space, but I will not be able to see the conversation in the space. So you don't need to add any of the teaching staff members. You guys can create spaces and then meet on regular basis to discuss. All of that I encourage. Now, in terms of YouTube channels, there are quite a few. There is one that I have created for this semester, which is the top link over here. And I've taught this course in the last two spring semesters. Spring 2020, the second half of the lectures are available on our YouTube channel, as well as for spring 2021. Now, if you want to kind of watch these ahead of time, you are welcome to do that, but I'm not going to require that. If you're curious, if you are, if you want to get some, head start, you know that these are available. All right. So what are the prereqs for this class? Well, essentially, COCO or LITEX material, or if you are coming from the computer science department, you might have taken computer organization. So I'm going to assume that you know about these topics: combinational logic design and sequential logic design. It includes multiplexers, decoders, encoders, adders, fast adders, comparators. So all these fall under the category of combinational logic design. And I'm going to assume that you guys know this. The reason is, once you start getting into computer design, organization and design, you need to know how a multiplexer works, because you're going to now see it a lot, right? In fact, you're going to now look at how do I use this multiplexer to efficiently design a data path to execute an instruction. So, that's something that I'm going to assume that almost everyone in this class is comfortable with. Also, with the sequential part, latches, flip-flop, registers, we are going to be using a lot of registers because the data path of a computer is, primarily based on registers. Our instruction set architectures are going to be based off of registers. So the conversation about how do you make flip-flops using latches, how do you make registers using flip-flops, how do you design state machines, all of those things, I'm going to assume that you guys know this. Now, the other thing that is sort of in the gray zone is the data path unit, control unit, and the instruction cycle. Now, depending on who you took COCO with, you may or may not have gone into these ideas about data path, control, and instruction cycle. Also, the last one, instruction set of a simple CPU. There's no need to worry. I'm going to be starting this discussion from scratch, maybe today. But if you depending on who you took the class with, you may or may not have been exposed to these ideas. But we are going to be talking about them, reviewing them in detail again. So there's no need to worry. But I'm going to assume the first point that you guys know this pretty well. So where were we and where are we headed? We were in this world, right? The COCO world. Things were very simple. Things were almost sort of discrete. They were not very well integrated. Maybe they started getting integrated when we started talking about finite state machines. However, we learned them in separate chapters, right? Separately. Muxes, and then decoders, and then latches, and so on. We didn't do too many things in which everything was involved. Everything was talking to each other. So that's where we are headed in CANOS. We are going to be designing and analyzing things that are applicable to the real world, right? So using the components that we learned in COCO. So what did we do in COCO? We talked about logic design. How do you design using logic gates? What do they have? Logic gates have transistors inside them. How do you design registers? Well, you take a latch, you design a flip-flop, and then using flip-flops, you can design registers. Buses, in order to talk between components, move data between components. The concepts of static and dynamic RAM. And we also did studios, at least, in my studios, you guys had designed a very simple 4-bit ALU, which can do some logical operations and maybe an addition operation. That was our simplified ALU. So that's where we were when we were talking about components, computer components and operations. Now what we are going to do is we're going to take all of that learning and move on to modern computing systems, which involved a modern processor, a hierarchical memory system. We didn't quite spend too much time talking about, cache, RAM, and a hard disk. They have different characteristics. For example, cache is small but fast. A hard disk is very large, but it is slow, dramatically very slow, actually. So significantly slow. So why do we have that hierarchy? How can we reduce access times to memory by playing with this hierarchy? So all of those ideas, the concept of virtual memory, we are going to be looking into that in CANOS. Multitasking operating systems, and then we will also move into networking. So when we look at operating systems, we will be talking about how is the file management happening in our OS. What are the different types? What are the different layers in an operating system? We'll talk about how does a CPU scheduler handle tasks? How does it ask a certain processor to work on a particular instruction? So, there are lots of interesting ideas when we get to operating system. So you will see this sort of progression in this class. So first, we'll start talking about computer architecture, where you are looking at this class in terms of designing the best data path, right? So how does the incomplete instruction cycle happen? What all do we need to do in order for a small set of instructions to be carried out? Do we need to have memory? Sure, we need to have memory. Do we need to have ALU? Yes. Do we need to have buses? Yes. Do we need to have a register file? Yes. So how are all of these connected? That will be our first goal. Then we'll talk about pipelining. Then we'll start talking about operating system and memory. But when we get to operating system, there will be a small change, right? Like the change will be now you're looking at things a little bit more theoretically, right? So what goes on behind the scenes in an operating system? What is a virtual operating system, virtualware, virtual machine? How does the file management get carried out? How does the resource allocation get carried out? So all of those interesting ideas in operating system. And then we'll talk about layered networking in terms of TCP/IP or the OSI model. Now, let's talk about the 8 great ideas in computer architecture. And the reason why these are 8 great ideas is because all of computer architecture is based on these sort of 8 pillars, right? And as you are designing, or if you're a computer architect, you are thinking about these ideas in order to make better systems for the future. Now, each of these ideas, they have a particular icon that is used in the textbook, and those icons are shown on the right over here. The first great idea is design for Moore's law. What's Moore's law? Well, it's sort of debatable, and there's a lot of conversation online about whether it is saturated or not. But in reality, Moore's law is the number of transistors will double every 18 to 24 months. So why is this important for computer architects and designers? Well, when you are designing something, designing a new chip, for example, it's going to take you a long time to do that, maybe a year, maybe 2 years. But by that time, Moore's law might have, given you something else. It has already doubled the number of transistors for that same amount of real estate. So as computer architects, you need to have that law in mind so that you don't design for the current technology, but you design for what the Moore's law is going to dictate after a year or 2 years, right? So design sort of for the future. We expect it to hit 2.7 or 1.5, sure. That is the theoretical limit, yes. But again, these kind of things sort of are very debatable, right? So I have never found a consensus as far as Moore's law is concerned. Earlier, there used to be, but in the last 10 years or so, there has been a lot of debate about whether we have already saturated the physical limit of how small our transistors can be and so on. Now, the next great idea for computer architecture is use abstraction to simplify design. And this is sort of, by the way, the symbol for Moore's law, the fact that you should be designing for Moore's law is a graph in which you are showing up and forward. That's your Moore's law. So whenever we sort of refer to this in the textbook, you should understand that that's what it means. It means that the designer is thinking about Moore's law and it is designing for it. The second great idea is use abstraction to simplify design. And this is something, an abstract painting is the icon used for that in the textbook. Andrew says, does that mean the CPUs being designed today are not possibly with the current technology? They are, right? Because when they started designing it, they designed it for the 5 nanometer technology, right? So it's during the design process that the computer architects need to worry about that, right? So if somebody is starting with today, they are going to be looking at if their product is supposed to come out in 2027, they are going to have to take into that account that 2.7 factor, right? So that's during the design process. Working with foresight, yes, that's right. Use abstraction to simplify design. We all do that, right? We all do that a lot of many times. Now, as simple as a logic gate. When you think about a logic gate, you don't think about transistors. We know that we had used transistors to make logic gates. However, when you think about a NAND gate or OR gate or NOT gate, you don't think about its transistors, you think about its functionality. And then you build more on top, so there are layers of abstraction. And the higher you go, the more simple your design becomes, right? So that's essentially the purpose of, say, for example, a top-level design, right? So if you had done the VHDL studios in Coco, you know that we design one module and then we design another module using the first one, and then you design a third module using the one below it. And then at the very end, you design the top level, which uses all the other modules, right? So when you look at the top level, things are going to be a little bit more simple and very easy to follow. And as you go down the hierarchy in terms of abstraction, as you go down, the design is going to become a little bit more detailed, hence a little bit more complex. So use abstraction to simplify design. That's the symbol for that. Wherever it is applicable in the textbook, you're going to see that symbol. Make the common case fast. We have a sports car symbol for that. Make the common case fast. And this is something that we all should learn from. I think it is applicable for us as engineers in things that are outside computer architecture as well. So what does make the common case fast mean? It means that things that are being done commonly frequently, you are going to try to make those things very efficient, as opposed to worrying about things that do not happen as commonly, right? So, in other words, don't be a perfectionist, right? Like that's sort of how I think of it. If you are going to try to tackle every little problem, even if it is not common, then you are putting in resources, your time, your energy, your computer resources in making things fast or making things efficient, where it's not even common. It's rarely going to be used. So try to make the common case fast. One example of this in terms of our instruction set architecture I can think of is, in your instruction set architecture, there are going to be some instructions that are going to be used a lot. For example, addition, right? Addition is used a lot, like add or move. Yeah, that's right. That's exactly right. That's exactly right, Andrew. So try to make that addition faster as opposed to a division, right? So try to make the instructions that are common, that are frequently used, faster, as opposed to worrying about things that are not so common. So we have a sports car icon for that. Next three are related with performance. Performance meaning number of instructions that can be executed in a given amount of time. Or it could mean energy efficiency, whatever that might be, however you define performance. Or it could mean lowest execution time for the CPU. You can get to performance, a high performance, using three things. One is parallelism. We have multiple jet engines on an airplane for that. So doing things in parallel. One thing that I would like you guys to note about parallelism is this. Of course, when you do things in parallel, you are going to improve performance, right? Then the amount of time taken to do a particular job is going to be faster if you do it in parallel. However, you should also note that there should be tasks that are designed for that, right? So if there is a particular task that cannot be done in parallel, then you don't get the benefit of improving performance. But if there is a task which has several sort of threads and you can run them at once or stagger them even, then you can get the benefit of parallelism. So, be aware of that. Parallelism is not just simply, doesn't give you the benefit always. The thing aren't threads for pipelining. Yes, so threads are for doing things in parallel. We use pipes for pipelining. We use pipes for communication between processes. So a thread is essentially to do a particular job in parallel. Pipelining is something else. Pipelining is more in terms of hardware. And that's next on the list, so I'll talk about that as well. But parallelism is, if you have a big task, if you are able to chop it up into multiple tasks, multiple smaller tasks, and then make progress on that, then you are sort of doing it faster. Multi-threaded is more faster and efficient than single-threaded, depending upon the instructions, right? So depending upon the tasks. Some tasks are very can take the benefit of parallelism. Some tasks cannot really take the benefit of parallelism because there's no gain, right? So either there is gain or there is no gain. I'll give you one example in terms of a MATLAB program, right? So a few years ago, maybe about 10 years ago, MATLAB had this parallel MATLAB option where you could take a very intense program, MATLAB program, and run it on multiple cores. But for that to happen, you actually had to change the code itself, right? So you had to actually code it differently in order for that to happen. Let's see. Next one is pipelining. And for that pipelining, we have a set of pipes that are connected one after the other as the symbol, as the icon for that. And pipelining is something that is very interesting. It essentially means this. You have several computer resources. Now, if a particular instruction is using one resource, are you going to wait for that instruction to get completed and then reuse that particular resource? Or as soon as the first instruction gets done with a particular resource and moves on, you use that resource for another instruction, right? That's pipelining. And in the textbook, there is a very good example about putting out a fire, right? So if you are trying to put out a fire, and say you are doing this by creating a human chain in which people are sort of passing buckets of water, and there is one person at the very end who is actually putting the water on the fire to put it out, what is going to be more efficient? One option is one person sort of runs back and forth with the bucket of water. That's going to take a long, long time. Versus you pass the buckets with the human chain, and every human that is in that chain is not going to be unutilized, right? They are always passing the bucket forward. They are always busy. It's not like they are waiting for the last person to dump the water on the fire and then they can pick up a new bucket, right? So that's sort of the idea of pipelining. In our case, we were trying to move, in the example that we talked about, we were moving buckets of water, but in our computer architecture, we will be trying to work on an instruction by using a particular resource in a computer. Maybe that's ALU. Maybe that is decoding an instruction. Maybe it is finding out what instruction it is and reading the memory. Or maybe it is saving the results of an instruction to memory. Whatever that case might be, you can do things in sort of in a pipelined manner. Next, performance via prediction. So we have a crystal ball for that as the symbol. And this essentially means there will be some times where it is better to predict what that next instruction is going to be and start working on that, as opposed to waiting and not working on anything. Because even if you are wrong, then you can backtrack. And the penalty you pay for that is smaller than waiting for that duration of time. This is how Apple got their Apple patiently. Yes. So this especially is useful when you're sort of executing a branch instruction, right? So if you're executing a branch instruction, then there are two possibilities, whether the condition of that branch instruction is met or not met. The condition is satisfied or not satisfied. So what you can do is you can look at the history. And when you look at the history and certain aspects of certain statistics of branching instructions, then you can base your prediction about what that next instruction is going to be based on statistics. And so you're predicting, and then you start working on the next instruction supported by the statistics. Most of the time you will be right, sometimes you will be wrong. And when you're wrong, then you can sort of backtrack and dump all your registers and restart that instruction. So performance via prediction is interesting, and we use that for branching instructions, and we'll see that. The next great idea is hierarchy of memories. There is a pyramid shown over here showing that there is a hierarchy, and the idea is this: everybody wants a fast, cheap, and big memory, right? So these are the three goals for a memory. It should be fast, it should be big, and it should be cheap. But these are competing goals. If you have a fast memory, then it is possible to have a fast memory if you have a smaller memory. and it is going to be expensive. So what you can do is you can take that memory which is fast. Let me reduce this. You can take a memory that is fast, make it small so that you don't have to pay a lot for it, but it is going to be expensive. And we call that the cache memory. And we'll put this right at the top of our pyramid. So when an instruction is to be executed, when a computer CPU generates an instruction, it will first try to look at the data for that particular instruction in the cache, the closest to it, right? So the cache is extremely close to the CPU. The bandwidth between the CPU and the cache memory is very, very high. So that gives it the speed, but it is small because you don't want to spend so much money on it because it is expensive memory. But as you go down, you have RAM over here and a very slow, cheap, right? So slow, cheap, big memory over here, all the way at the bottom. So if you don't find things in the cache, look in the RAM. If you don't find things in the RAM, look in the hard disk. If you don't find things on the hard disk, maybe you look into a server that is connected on a network to your computer. But by doing this hierarchy, what you are doing is really giving an illusion to the user that you are actually using a fast memory, which is cheap and big. So that's sort of the illusion that you're giving to the user. And in the middle, you can also add some SSDs, and we'll do some examples where we'll see how we can increase the number of levels in our hierarchy and reduce access times to memory. So we'll do all those problems later. The last great idea is dependability via redundancy. So if you want to have something dependable, then one way to do that is to have redundancy built into your system. And we do that even for a lot of things. We do that every day, right? So if you have a primary computer, then you also have a backup computer, or you back up your data. Similarly, if you are thinking about storing things to memory, when you store and retrieve information from a memory, you can try to build some redundancy into it, maybe by using certain parity codes, for example, Hamming parity code. And what that allows you to do is, it is redundant, right? It is those parity bits are not information, but they are essentially used to do some error control or error detection, and maybe even correction possibility for your data that you're storing. So we have a trailer truck with multiple tires as the symbol for that. So if one tire goes out, you have the other tire as the redundant tire to at least take you to the next service station. All right, so these are sort of your great 8 ideas, and we'll see how these are applicable to our computer architecture operating systems course as we go through these through the lectures. Okay, let's see. Computer abstractions. Like I said, computer abstractions are everywhere, from logic gates to flip-flops to all the components that we have learned. Abstraction is there everywhere, and even now, right? Like right now, you may be using a laptop. In the laptop, you are running an application software. But as you are running an application software on your laptop, you are really not worrying about all the layers that are beneath it, right? So there is a system level software that is underneath it. There is an instruction set architecture, maybe based off of x86 underneath that. There is microarchitecture, there is a digital logic, and below that even there are transistors that make up your device, right? So there are lots of things that are supporting that application software that you are using currently. However, the user doesn't, those are all transparent layers. However, they are very, very important layers. And the idea for having all these layers is mainly to divide and conquer. So you are, instead of having a flat structure or no structure at all, what you can do is have a layered architecture so that if some element goes wrong, you know where to look for. It also brings modularity into your design. It also brings, all you need to worry about is the interface, right? So layer to layer interface, that's all you need to worry about. After that, you can sort of divide all the functionality of your complex design into simpler, smaller layers. So that's for a computer in general. We will be working on the ISA layer quite a bit in the beginning. Over here we have ISA. Let's see. And the instruction set architecture, instruction set we will be working with is MIPS, which stands for microprocessor without interlocking pipeline stages. There are other instruction set architectures as well. There is, what is that, x86, of course, the Intel-based x86 architecture, which is very popular. However, there is so MIPS is actually a modern RISC, but we have RISC as well, yes. And then we have, of course, ARM. And I don't know which version of ARM we are currently in. Maybe V10. ARM V10 is what we are using for the iPads. ARM V8. I think we are doing ARM V10 maybe for the iPads. At least for the current iPad that just came out. ARM V9. Okay. Was being okay. Yeah. So we will be here. We will be in the MIPS world. And the reason why we are doing this is because x86 is sort of more complex ISA than MIPS. So in terms of learning about an instruction set architecture, MIPS has all the advantages. March 30th, ARM V9 came out. Okay. So maybe you say V8 and now V9, right? Okay. So we will be using MIPS. Now, one thing that I want to point out about MIPS ISA is there will be instructions, there will be registers. It is an assembly language, right? Essentially, it's an assembly. So you guys will be expected to write these instructions by hand. What I would recommend is look for good simulators. There will be MIPS simulators online. And MIPS simulators. The one I use is Mars. It is free. It's a Java runtime environment. Do we have to know the entire instruction set? No. So we are not going to learn the entire instruction set. We are going to learn at least the integer instructions. We will try to learn them. We will not get into the floating point instructions. So the a really good way of learning an ISA is to work with a simulator, see how the instructions are run, and you can monitor the memory while you are running these instructions. So that is really good. And I, from later on in the course, when we get to the right time, I will be giving you guys some demos. But this is something really that you guys can do by yourself. There are plenty of resources online. It is not a required part of this class, but I recommend you to use a simulator to improve understanding. Don't pay any money for it. They are free simulators out there, very good ones as well. So if you don't want to search around for that, just go for Mars. I'm not sure whether they have a Mac. Oh, Java runtime. Yeah, sure. You should be able to do it on all platforms. All right. Next, in terms of languages, they are layered in terms of even languages, right? So if you look all the way at the top, you think about an application software, maybe Java, Python, C++, C Sharp, MATLAB. All of these are way at the top, and we are so used to writing code at the application software level. But underneath that, again, there are many layers. So there is low-level system software, which comprises of assembly language and C. Underneath that, you have the instruction set architecture, which involves machine language. So this is binary microcode language, a bunch of zeros and ones. So essentially what's going to happen is a compiler is going to take your application software and convert it into assembly. And then later, an assembler is going to take your assembly language and translate that into machine language. And then it becomes a bunch of zeros and ones, which your computer can understand and work on. Underneath that ISA, you have your microarchitecture, which essentially involves RTL, Registered Transfer Language. And some of you may be new to RTL, but essentially what this means is to carry out a bunch of instructions, you will need to move contents from one register to the other. And as you are doing that, you can write that particular movement from one register to the other in a RTL format. Move contents of accumulator to move contents of accumulator to memory, right? So that's a RTL language. Underneath that, you have your digital logic, which comprises of all your Boolean algebra and state machines that we talked about. So when you're working on this top layer, all of these underneath layers that are transparent to the user, they are doing an effective job, but the users are sort of all the way at the top here. User is over here. Now let's take a quick look at how this high-level language and assembly language and the bits work, right? So all the way at the bottom here, we have your machine language, or your this is for ARM v8. We will be using MIPS, as I said, but these are a few instructions. They are 32 bits at a time, right? Now, if you look at this, a computer which is based off of the ARM v8 is going to be able to work on these instructions, but we as humans will not be able to interpret these instructions, right? They are a bunch of zeros and ones. What do they mean? I don't know. What are they? They are an output of an assembler. How did you get it? Well, somebody wrote an assembly language program which looked like this. Swap is indicative of some memory location at which you have all these instructions, some branch instructions, some add instruction, and so on. These are working on certain registers, contents of certain registers. So this is assembly language, right? So this is sort of readable, somewhat readable. Maybe we will be able to follow along. So if you are asked to write a bunch of instructions in assembly, you could, but it is still not going to be as easy as writing in a high-level application software such as in C, right? So in C, which is a syntax-based language, you can write in commands which are sort of algorithmic, right? So it's a user-friendly, it's supposed to be user-friendly language. It's a high-level language. It is portable, right? So I can take this C program and port it to across different platforms and use the right compiler to give me an assembly code for ARM v8 or MIPS. So that's the reason why your high-level language is portable, right? So you can take one and move to the other. So a user is going to be very comfortable writing in the high level. So a compiler translates, the job of the compiler is essentially to translate your C program into an assembly language program, which looks like this, and then the job of an assembler is to take that assembly language program and translate it into a bunch of zeros and ones, which the computer can understand and work on. Now, for this particular instruction, for this particular example over here, let's see, we have an add instruction that is shown over here. It is, I think it's taking the contents of x0 and the contents of x10 and adding them up and putting the results in a register called x10. So that's the command, right? But if you look at it, the same command in assembly, it's there, right? Now, of course, we have learned that an assembler does this job, but how did things begin, right? Like how did we get there? Well, when all of this started, machine language was being written by users in machine language, right? Like people used to write code in machine language. Then it became very, very tedious. Of course, I cannot write zeros and ones, bunch of zeros and ones, right? For one instruction, I need to write, say, 32 bits of code for one instruction. That is not very convenient. So then we moved to assembly. And then even that became a little bit more tedious, because to see it in a very algorithmic way, it's not that straightforward. You go one level up. You say, all right, I'm going to write it in a high-level program. A compiler can translate that into assembly. An assembler can translate that into machine language. Now, as we go through the first sort of 10 lectures, you guys will be comfortable with doing this. Going from high level to assembly by yourself, and going from assembly to binary machine language. For MIPS, you should be able to do that. And if you can go one way, you can obviously go the other way as well, right? So that will be sort of our goal for the first few lectures. 32-bit, yes, MIPS. We'll talk about MIPS 32, not MIPS 64. So we'll do a 32-bit instruction set architecture. There is MIPS 64 as well, but we will be doing MIPS 32. Let's see. We talked about high-level language. How does that bring in abstraction? It is portable. Assembly language is essentially textual representation of instructions. These are not understood by a computer, right? So we still need an assembler to translate that into binary code. Wait a second, is this architecture for learning, or is it actually used in the industry? I've never heard of it. Okay, so ARM v8 or MIPS, it is just for learning. MIPS, yeah, it is just for learning. So suppose you want to be a computer designer, right? So it's something like VHDL and Verilog, right? So we learned VHDL in Coco. We didn't learn Verilog. So if there was a requirement for you to learn Verilog, you would be able to pick it up very quickly because you already know one hardware description language. So MIPS and x86 and RISC, ARM v8, these are all they all also face the same situation. MIPS is pretty easy to learn and follow, but once you get a command over MIPS, you can go to x86 and the other instruction set architectures pretty easily. So that's the reason why generally you have MIPS, or in some schools RISC is taught. It becomes very tedious to teach x86 in school. So if you are really interested and this is your thing, then I'm going to recommend that you go ahead, maybe during this summer semester or after this summer semester, expand your understanding on x86 architecture. But we are not going to be dealing with that during this course. We'll be doing MIPS. Sure, yes, that your argument is very valid, and I agree with that as well. The reason why I said x86 is because it is the most popular one, right? So everybody understands x86. So one of the other reasons why I mentioned x86 is because students, when they go to interviews, they get asked about x86. That's the reason. But sure, you know, you wouldn't be picking up a bad choice if you start your investing your time in ARM ISAs. All right, let's move on to the layered approach. Like I said, it's all about divide and conquer. And the idea is to design and build complex system one layer at a time. If you start at the bottom, then you can't really start at the bottom, right? So you start with the complex system, and then you put layers of abstraction on top of each complex layer underneath, so that you do this divide and conquer and also simplify your design by putting up layers of abstraction above it. So what did we do in Cocoa? We built gates using transistors, we built combination logic using gates, and then we designed sequential logic using combinational logic and registers. And then at the very end, we put all of those combinational and sequential logic to build memory and ALU, or even the state machines, right? So looked at transistors all the way at the bottom, and we looked at memory, ALU, fun state machines all the way at the top. So we built on to things as we went on. So we did a layered approach even there, and that was for that same purpose, to divide and conquer. And you will see all three aspects of our course having that layered approach, whether it be computer architecture or your networking or the operating system. For operating system, the layers are the user interface all the way at the top, and the system kernel, the core of the operating system, way at the bottom. And in the middle, you will have layers for file management. How do you create files, organize files, store files, backup files? What are the different options depending on different operating systems? The next layer being input output. So how does your input output peripherals communicate with your CPU? How does the interrupts happen? How does the data transfer happen, and all that? Underneath that, there is memory management. So what do you do with open or free blocks of memory? How do you manage free space? How do you allocate space for certain tasks? So all of those things fall under the category of jobs operating system is supposed to carry out. So we will be looking at all these layers in a good amount of detail when we get into operating systems. Let's see. For the network layers, and we will be essentially looking at TCP/IP and OSI models, the two popular ones. You will see some variation of this, but in general, you will see these 5 layers. All the way at the bottom, you have the physical layer, and all the way at the top, you have your application layer, for example, an email client, web client, or a web browser, for example. So when you're looking at the physical layer, most electrical engineers are sort of in this world, the physical layer. Because if you're talking about the wireless communication, then you're looking at the wireless medium as your physical layer. If you're talking about an Ethernet network, then you're talking about an Ethernet cable as your physical layer. If you're talking about a optical communication link, then you're looking at the optical fiber as your physical layer. So all of these are essentially a bit pipe, right? So take a bit sequence and relay it from one end to the other end of your pipe. So that's your physical layer. Above that, there is a data link layer, which has the responsibility to do error control and also for media access control, or the MAC address that you see on your devices. Above that, you have your network layer. So it deals with packetization, addressing, and routing. Above that, you have your transport layer, which maintains end-to-end connectivity. And above that, you have your application layer with the email client and the web browser. The one thing that I would like you to note is this. As the communication is happening between, say, device A and device B, the bottom 3 layers are actually looking at the actual communication, right? So At each router that is placed between a computer A and computer B, all of these things are being sort of looked at. The bottom three layers look at everything that is being communicated between computer A and computer B. The top two, they don't. So the top two only come into picture at the very end, at the end to end, right? So if you want to relate to sort of the bottom three layers, it's IP address that falls under the purview of network layer, then the MAC address that falls under the purview of data link layer, and then you have your port number that sort of falls under the purview of the physical layer, right? So that's essentially what you do to communicate between devices using a network, whether it be a wireless network or a wired network. All right, let's see. We have, it's 9:20 right now. Maybe I will try to get a head start on class 2. So the deal is this. In a regular semester, there are 26 lectures. In summer, we have 21 lectures. So I need to use every class to gain 5 lectures end to end. So what I'm going to do is I'm sort of going to complete one and maybe get a head start on the other. So that's what I will do, maybe for a few more minutes. And then I'll give you guys some time to work on the activity. Not too difficult. It's a review of COCO, essentially. So if you're not able to do it in the morning today, you can use the office hours later on in the day to complete your activity. All right. So let me spend a few minutes talking about the basics of a microprocessor. So this is, for some of you, it might be sort of a review of COCO, but for some of you, it might be absolutely new. But in any case, it'll be a review for you if you have already seen these things. The readings for this are from Patterson and Hennessy, sections 4.1 to 4.4. We will be going in quite good detail when we talk about the microprocessor basics. So the building block is a register. And if you think about a register, it will have a few inputs and outputs. So you have data that you want to store into the register as an n-bit input indicated over here. And the data that you want to read from a register, you can see that as an n-bit output over here. By the way, if you had to design a register, what are you using to design a register? You have all the choice. What are you using to design registers? D flip-flops. Excellent. So, bunch of D flip-flops are being used to design registers. What we are going to be using or seeing is a 32-bit register. We'll be seeing 32-bit registers in the MIPS ISA. So that essentially means that we have 32D flip-flops built into that one register. So you can put data onto it and you can read data from it. You can write data to it and you can read data from it. So maybe I can also write this. This is your write and this is your read. But in order for you to read and write, you need to be able to use these controls appropriately. So for example, there is a load. When do you use a load input? Well, there is a control input that can be used to write data into the register. And then output enable is a control signal that you can use to read data from the register. In order to run the code, is there a compiler for MIPS into your architecture? Like, there should be. So MIPS is already assembly, right? So if you're looking at zeros and ones, then you're looking at an assembler that gives you your MIPS to a machine. All right. So again, output enable, another usage of output enable is what? You can use this to connect multiple registers onto one bus, n-bit bus in this case, right? So you can use output enable for that. So these controls, load and output enable, actually come from the control unit in your computer. And the data in and the data out, these are essentially coming from the data buses, which are part of the data path unit. So let me also sort of highlight that as well. So these are coming from control unit. There was no cascading. There was just one 32-bit register that we talked about. You guys should be a little bit comfortable with cascading, because now we are talking about a computer design, right? Computer architecture. So, of course, there is going to be a cascading. Registers can also be shift registers. So you can also include these shift controls for a register. You still can write to it. You can still read from it. You can load data into the register. You can make the output enable active so that you can read data from the register. But apart from all these, you can also have shift controls. You can move things left, right, or maybe no shift at all. So for that, you would need additional controls, again, coming from the control unit. That's right. So all the control signals are from the control unit. All the data carrying buses are part of your data path unit. So registers and buses, those are your main components of data path unit. But all the other controls are coming from the control unit, which is sort of the biggest finite state machine. Looking at what operation is being carried out and then sending control signals to the appropriate locations in your computer. The next building block is your ALU, arithmetic logic unit. So sort of the workhorse in your computer architecture. Now, an ALU is a combinational circuit. There's no feedback. It takes input B, depending on the opcode. This is sort of your opcode. Again, this is coming from the control unit. Look at the particular instruction, and depending on what the opcode is, send a control signal to the ALU, letting the ALU know it is supposed to add right now. So ALU A side, an n-bit input. ALU B side, an n-bit input. Take these two, generally a 32-bit input for us, work on the instruction. Maybe it is add, multiply, shift, load. No, not load. For loading, we don't need ALU. Maybe shift, maybe divide. All of those, maybe exclusive OR, maybe all the logical operations. Do any of those, and then send two things as the output. One is your n-bit result. You may be interested in storing it onto memory, or you may not. But whatever. There's an n-bit output for that ALU, as well as certain flags, which can be monitored by the user to know whether or not there was a carry out. Maybe you were adding some things, two numbers, and you were looking at the most significant carry or sort of the carry out of the signed positions if you are doing signed arithmetic to find that out. Or you are looking at detecting overflow, or you are looking at is the result 0 or not, or you are looking at whether the result is positive or not. So you could be, what if there are no flags? No, flags are always there, right? So flags is sort of, um, think of flags as a 8-bit register, and there's a flag for each output, right? So there is a bit for carry out, there is a bit for overflow, there is a bit for result being 0 or not, there is a bit for whether the result is negative or not. So there is a position for each flag bit. If they are inactive, that means that that flag is not raised. If they are active, that means that flag is raised. So you can use that accordingly. The one common flag that we will be using is the 0 result, right? So the 0 result is actually very interesting. As the flag, because we can use this for comparison, right? So what we can do is we can say, okay, subtract this number from this number, and if it is the result is 0, then carry out this particular instruction, or do this based on that 0 result. So that's where you could use that particular flag. Let's see. Yes. Now, as I said, we also need buses to move data from one end to the other. And these buses can be of 3 different types. One, you could have data lines, which are two-way buses. And in this case, we are showing that the two-way buses are n-bit. Those are data lines. Then you have address lines, only for only one way, and they are m-bit buses. Why are address lines one way? Nice. Okay, I think there is a relevance to the actual answer as well. So if they are one way, let's talk about this. If the address lines are one way, where are they going to? There is only one component that understands address, which is a memory, right? So it is going to memory. And when you think about memory, what can you do with a memory? Only 2 things. Either you can read from the memory or you can write to the memory. For both of them, it is going to need an address. But that address is only going to be directed towards the memory. Because there is no need to send address backwards. Sure, that's exactly right. It's unnecessary for them to be both ways since they only need to send data, not data. So address lines need to only go one way because there's only one component in our computer architecture that understands memory, that understands address, which is memory. And you can use these address lines to read from memory or to write from memory. Well, when should I read and when should I write? That depends on the next set of buses, which is the control lines. So if you it allows other registers to know where to send the data. It allows the registers to know where to send data. So you're trying to move part of the memory, right? So suppose there is a particular location in the memory. It's a 32 bits data at a particular address location in your memory. If you want to move that to a particular register, then you need to give an input to the memory through the address lines. But that address line is only going to the memory. You see that? So the instruction is generated by the CPU, and then the instruction is actually in the instruction memory. You read that instruction, you decode that instruction, and then you send the particular address location to the memory. But it is only going to the memory. There is no address going the other way, because only one entity understands an address, memory. Let's see. Right. Next, we were talking about the control lines. Why do we need control lines? To load data into a register, to output enable or read data from a register, to ask our memory to read or write, right? So along with this address line, we also need to inform our memory that we are now interested in reading you, or we are interested in writing to you, right? So all of that goes into the control lines. Even these guys go into the control lines, by the way. The opcode also is part of the control lines. So these are data. All of these are control. Load, output, enable, and all that. Will the opcode go into the control line? Yes, it does. Yes. No problem. Now, in terms of rules, we have 3 rules to sort of keep track of. The first rule is only one device can write to a bus at any given time. Sure, there should be no argument about this, right? When you're writing to a bus that is being shared by multiple registers, then only one entity can change the contents of the bus so that there is no corruption of data. So only one can write to a bus at any given time. The second rule is multiple devices can read from it. So no problem. As when you're reading it, multiple can read the contents of the bus, because the reading is not going to corrupt it, writing is going to corrupt it. What that also means is this. There are going to be limitations on the load and output enable signals because of the first 2 rules. When you are moving data from a bus, let me do this. When you are moving data from a bus to a register, you are essentially reading it, right? So you can have multiple load signals active at any given time. However, when you are moving data out of the register, maybe you are reading the register and you are going to a bus, you can only have one output enable signal that can be active, right? So rule 1 and rule 2 actually impose restrictions on the load and output enable signals for the registers. Okay, sorry. And then rule 3 is there is usually a bus protocol that is followed strictly by all the devices that are sharing the bus. Who is going to share it when? Is there priority built in? Are we going to do a ring formation? So that's your bus protocol that is agreed upon by all the devices that are communicating on that bus. Now, let's talk about the 3 registers sharing a bus. We have register 1, register 2, register 3. These 3 registers are sharing the data bus. We have a data bus over here which is n bit wide. We have an address bus which is m bit wide, which is not playing any role in this particular example. And then we have c bit control lines that are actually playing the biggest role in this particular example. So suppose you wanted to move contents of register 1 into register 3. What are you going to need to do? Well, if you want to read the contents of register 1, then are we doing right? So suppose you want to do this. You want to move R1, contents of R1, you want to move to R3. Do these registers have tri-state buffers built in usually? Yes, we need, because they are sharing. Every time you hear the word sharing, you know that there is tri-state buffers that are involved, because we need to allow only one thing to write to the bus, and so that we are able to disconnect all the other things. Alright, so suppose we wanted to move this, right? We wanted to move the current contents of register 1, R1, to R3. Each register has two controls, which is load and output enable. Load, output enable, and so on. Now, if you want to move R1 to R3, first you would need to move register 1 to the data bus, and from the data bus you would need to move to register 3. So in terms of RTL, register transfer language, you would be writing this: R1 to bus, in this case the data bus, and then bus to R3, right? However, for these to happen, you need to have the appropriate control lines. For example, if I want to move contents of register 1 to the data bus, then I need to activate output enable 1, right? So I need to make this guy active, but I have to make sure that all of these are inactive. Output enable 2 and output enable 3 are inactive. Next, once I do that, I will be able to read the contents of register 1 out on the data bus. After that is complete, I need to now move that into register 3. So I need to load that into register 3. I need to write that into register 3. Now what do? I just enable the load 3 signal. By doing that, I would have moved it into register 3. I'm a little confused how the OE and loads are determined by control lines. If it's a bus, wouldn't they all get the same signal? So it's a bus, but load 1, load 2, load 3 are all different, right? So think of load 1, load 2, load 3 as 3 different signals as opposed to 1. Why isn't register 1 not writing to the bus and then register 3 reading from the bus? That's exactly what we are doing. So here, reading and writing are relative, right? So the first thing that we are doing is we are writing to the bus and then we are reading from the bus. But you see, when I say reading from the bus, I'm actually writing to the register, right? So think of read and write in those relative terms. What I'm really doing is this. If I was just to base all the statements off of the bus, then I am reading from the bus, writing to the bus and writing to the bus and reading from the bus. You guys see that? All right. So yeah, when you were reading from the bus, you could have had load 3 enabled. Sure, that's what we need to do in order for our register 1 to get transferred to register 3. But if we were wanting to do this for even register 2, we could have done that. We are not doing that right now, but we could have done that. So there is no particular requirement that load 2 should be inactive, because when you are reading from the bus, you can do multiple at a time. Let's see, wouldn't it be possible to read to 2 or more registers at the same time? Seems like it would same time. Well, it should support your instruction, right? So it should support a purpose. No. So when you are moving things from the data bus to a register, you can do multiple at a time. So you can move data from the data bus to register 3 and 2 at the same time. However, it should be supporting your instruction. If it is not supporting your overall instruction, then there is no point. You see that? So every instruction has a set of things that need to happen in order for its complete execution. And all of those things are necessary things, right? Like it's not like, oh yeah, let's do it because it uses something. You do it because it supports your goal. All right. Will fan out be a problem with the here? All of these things are designed in such a way that we don't have to worry about fan out. So we worried about fan out in the lower levels, right? But as now you are in terms of your abstraction, we are working at a higher level than that. So we are not worried about fan out for this. It is assumed that whoever designed it has designed it for fan out not to be a problem. Right, that's right. Okay, let's see. That's what we did, right? Move register 1 to register 3. What did we do? We made output enable active first, thereby moving contents of register 1 onto the data bus. Then we activated load 3 in order to move contents of the data bus into the register 3. Now let me ask you guys this. How many bit is register 1? That's right, n bits. Even this guy should be n bits, right? And the reason for that is because the data bus is n bits. So in terms of register 1, 2, 3 data bus, they all need to be consistent. But in terms of addresses, we are going to have an m bit address that we can read from or write to with respect to the memory. And then we have C control lines. 3 of them are load 1, load 2, load 3. And the other 3 of them are output enable 1, 2, and 3. All right. Let's see. Now, this is going to be sort of my last slide that I'll talk about today, which is when you are interacting with your memory, you are dealing with 2 registers. One is memory address register and the other is memory buffer register, also called as memory data register. Memory data register. So MBR or MDR. It's usually one or the other. There is a specific purpose for MAR and there is a specific purpose for MBR. So let me step back a minute and talk about memory. When you think about memory, what all can you do with a memory? Store stuff. Okay, let me see. Store stuff. What else can you do with it? Read from memory. All right. Okay, I think this is it, right? Store stuff and read stuff. That's it. So the next question is, for both of them, the next question is where? Where do you want me to store stuff? And where do you want me to read stuff from? Address and data. That's it. There are only 2 things. So where means address, right? In our case, an m-bit address. So our stuff is data. We can either store data or read data. But where are we storing to or reading from? That depends on the address. So only 2 things. One is the address and the other is the data. 2 things. So the names now give it away, right? Memory address register is a register where you are going to store an address that you want to read from or write to. And then memory buffer register or memory data register is going to be the register in which you will have data. Now, in the case where you are storing stuff, then you will put the data to be stored in MBR. And when you are reading stuff, you will get the data that you just read into the MBR, right? So this is sort of for the stuff, and this is sort of for the address. You guys see that? Next, I'm going to ask you guys, what is the size of MAR? Number of bits in MAR equals M. Exactly right. Is there a separate register for data output when reading? It is part of the memory itself. So that's a good question. Is MBR outside the memory? MBR is usually inbuilt into the memory space itself. But for us to understand all these things, we are sort of looking at it separately. M bits is right. How about MBR? What is the size of MBR? N, exactly. So when you're talking about MAR, you're talking about an address where you want to read from or write to. Both of them. Both operations, address goes there. And both operations, data goes here in MBR. When you're storing stuff, data will go from here to here. And when you're reading stuff, data will go from here to here. Now, there are certain memory control lines that you will need to send or receive from the memory. Does M equal something specific, or is it just to show that address and data aren't the same? Yeah, it is just to show that they aren't the same. They don't necessarily need to be the same. Let's just put it that way. They may be the same. It depends on how your memory is organized, right? So M, 32 or 60, that's right. But it really depends on the organization of your memory. But it could be different. It definitely could be different from N. But one is for address, one is for data. All right. So let's talk a little bit about the control lines. We have the chip select for the memory. Why is that? Well, because your RAM could be several chips, right? If you have ever built a desktop by yourself, you know that you could have many slots. You could have, say, 4 DDR4 slots in which you can have multiple RAM cards. So that is to select one chip versus the other. That's the control there. Next is your read and write, because that's what you can do with a memory. You can either read from the memory or you can write to the memory. But these controls are only going from the control unit to the RAM, to your memory. And then there is one signal that is actually going back from the RAM to the control unit, which is the wait. That is essentially used when the RAMs are slower. So the RAM is saying, all right, you are sending me these requests to read and write too fast. You need to slow down. So it would indicate that to the control unit by sending a wait interrupt back to the control unit. All right, so when you think about memory or RAM, that's what you're thinking about. You're thinking about MAR, you're thinking about MBR, and the fact that, even with the memory, you can go one level down and talk about instruction memory and data memory, right? So instruction memory would be a space where you would have all your instructions, and then data memory would be where all your data is supposed to go. Would the signals be C bits long? Well, all of these are sort of part of the C bits, right? So all the control unit, these are all controls, right? So there are 3 of them here: load, output enable, what else we have? Opcode. So all of these things combined are C bits long. But like I've mentioned, a control unit, so clock is everywhere. but we are not showing that explicitly at all places. But there's a clock, there's the master clock that is keeping everybody in sync, all the components in sync, registers, RAM, control unit, all the buses, everything is being clocked using one master clock. We are not showing that here just because it's everywhere. Let's see. Yeah, I think. All right, so let me stop over here. I'm going to stop recording, and then on Thursday when we meet in Low 4050 or on Webex, we will continue with our lecture. We'll start talking about the key concepts to build a computer. I'm going to stop recording. In-person classes, yes. Please get your COVID testing done on campus. I think most of you, are you guys required to do that, or is it optional? I think it's required. Yeah. So hopefully I can go the first week. Cool. Required until end of June. Okay. All right. So I'm excited to see you guys in person on Thursday. We have a few minutes right now, so you guys can get started with the activity. But I think you guys should be pretty fine with the activity. One thing that I would also like to point out at the end is I've attached a very detailed syllabus on Piazza. So later in the day or later in the week, you guys should take a look at it. I have discussed all the main points of the syllabus, but a detailed syllabus is also present over here if you want to read through it. Let's see. Yeah, and that's about it. So I'll see you guys. I'm going to be here. I left my Cocoa notes back home. Is there a way you can ask them to be sent? It's on Piazza, yes. Bennett, you have a nice day as well. Maybe I'll see you in Signals in a few minutes, or maybe not. You guys have a good day. All right. Don't forget the activity, guys.